This is section 17.3, and in this opportunity we will discuss about titrations, particularly involving strong acids and strong bases. So to begin with, let's review what a titration is. Titration, simply put, is a chemical reaction that you conduct between two different substances. You need an indicator so that you can determine when the reaction is complete. But the main goal here is to find out what the concentration of the analyte is by using another solution of known concentration. At this point, you know what the chemical identity of the analyte is, and you use the corresponding substance. For example, if you want to know what the concentration of an acid is, well, the acid will react with a base, therefore you use a base of known concentration to determine that the concentration of that acid. Okay, you use an indicator that allows you to determine when the reaction is complete, and at that point, when the reaction is complete, you will know what volume of the acid of unknown concentration you were using. You would know what volume of base you used, and based on the stoichiometry and the molarity of those solutions, of the known solution, then you can figure out what the concentration of the acid is. And the same thing goes if you are titrating a base. You use an acid of known concentration in order to determine what the concentration of the base is. When you are titrating a strong acid with a strong base, basically what you do is to make a graph of how the pH changes as you add the base. So it's a graph of pH versus volume of base added, and we can clearly identify 4 regions in this plot. In the first region, what we're going to call region A, that's basically the initial pH of the solution, and at that point the initial pH of the solution is, let's put it this way, is controlled by initial acid. More specifically, the initial acid concentration. Okay? As you start adding base while the acid is reacting and is being consumed, so region B, okay, when you still have acid left over, that region corresponds to points between the initial pH and the equivalence point. And at that point, or in that region, the pH is controlled by the leftover acid. Okay, whatever concentration you have at that point, it's controlled by the acid. The third region, region C, is the equivalence point. At the equivalence point, pretty much the concentration of H plus is equal to the concentration of OH minus. Okay, and because it's a strong acid and a strong base, there is no acid-base equilibria, so this relationship here is true. And because acid base at this point, we are working with a stoichiometry 1:1, okay, then the concentration of the acid is equal to the concentration of the base, or the number of moles of acid is equal to the number of moles of the base. Therefore, that relationship stands, and the pH at the equivalence point is equal to 7. Just to make sure, this is when you have strong acid, strong base combination. Whether you are titrating an acid with a strong base, a strong acid with a strong base, or you are titrating a strong base with a strong acid. So when you have this situation, then at the equivalence point, the pH is going to be equal to 7. And region D, the last region, is after the equivalence point. At this point, all acid is gone, and the pH is controlled by the excess base. Okay, therefore, what you have here is actually the pOH. So you calculate first the pOH because of the excess of base, and then pH with that equation. Okay. So this is how a pH titration curve looks like. Okay, we have here region A, initial pH, Okay, region B actually extends all the way there. Okay, so that part is controlled by acid. This is the equivalence point, and the one thing that you have to keep in mind is that this is pH 7. Okay, and from here up, at that point, all the acid is gone. This region is controlled by base. Okay, so that's how, and we have to be specific here, is strong acid, strong base curve. Okay, so how is this useful? Well, you have to calculate pH, or you have to be able to calculate the pH in any point of that curve given the proper information. So in this particular problem, we have 25 milliliters of 0.255 molar hydrochloric acid. You are titrating that with 150 molar solution of strong base KOH, and we want to determine the pH at all these points. Okay, before you add any base, after you have added 4 milliliters of the base at the equivalence point, and after you have added 50 milliliters of the base. Okay, so one thing that you have to keep in mind here is that, number one, you have an initial volume. Okay, and you add another solution. Okay, therefore volume changes, and if the volume changes, you need to adjust. Let's call it adjust concentrations, because it's not as simple as just to say you are not exactly diluting here. Okay, there is also a chemical reaction going on, but you have to consider how the volume changes when you are calculating your concentrations. All right, so let's start with A. Okay, before we add any KOH, so before you add any KOH, the concentration of HCl is going to be equal to the concentration of H plus, because in water HCl will go to H plus plus Cl minus. Okay, this is not an equilibrium reaction, this is a strong acid, so it's completely ionizing water, and this is going to be equal to 0.255 molar. Okay, no need to use any volume here, it's just the plain concentration that you are being given. That's the initial concentration, that's the one that you're going to use to calculate pH. So pH is minus log of 0.255, and this is equal to 0.593. Okay, 3 significant figures. Let's keep using 3 significant figures here. Now the story is different when you have added 4 milliliters of KOH, and at this point, well, you need to know how many moles of each, the acid and the base, you have here. How many moles of the acid you have? Well, first of all, you need to convert this to liters. So this is 0.025 liters, and then we have 0.255 moles of HCl per liter, and this is equal to 0.006375 moles of HCl. And for the base, you have 0.004 liters times 150 moles of KOH per liter, and this is equal to 0.0006 moles of KOH. Okay, so leftover acid, leftover HCl, it's gonna be, because the reaction is 1-to-1. Okay, so basically you consume this will react with 0.006 moles of HCl. So the leftover acid is going to be the difference, 0.006375 minus 0.006. This is equal to 0.005775. Okay, now these are moles of HCl, and you have to divide that by the final volume. The final volume is equal to 0.025 plus 0.004, which is 0.029 liters. So the concentration of HCl, which is going to be equal to the concentration of H plus, is 0.005775 divided by 0.029, and this is equal to 0.199 molar. Therefore, pH is minus log of 0.199, and this is equal to 0.701. Okay, so you need to determine what is the remaining acid in the solution after you have reacted with certain amount of the base, and then you proceed to calculate the pH. At the equivalence point, the concentration of HCl is equal to the concentration of KOH, okay, in the solution, which means H plus equal OH minus, and therefore pH is 7. So actually no need to do any calculation here. If you see that situation, if you are titrating a strong acid with a strong base, pH is 7 at the equivalence point. No need to do anything else. Now after you have added 50 milliliters of solution, okay, so remember it's 25 plus 50, so you have a final volume of 75 milliliters. Let's just keep that in mind, equal 0.075 liters. Okay, same thing, we already know based on the previous calculation that we have initially 0.006375 moles of acid. Okay, we have 0.006375 moles of HCl to begin with. So let's calculate how many moles of KOH we have added. So 0.050 liters times 0.150 moles of KOH per liter, this is equal to 0.0075. Now if we are past the equivalence point, and we know that because now this number is larger than the initial acid, okay, so the excess KOH is going to be 0.0075 minus 0.006375, and this is equal to 0.001125. Now this is KOH, which is equal to OH minus, so the concentration of OH minus is equal to 0.00125 divided by 0.075 liters. Okay, we have determined that this is the final volume. You added 50 milliliters to 25 milliliters of solution, so this is 0.0150 molar of OH minus. This means POH is minus log of 0.050 okay, and if we go straight for it, pH is 14 minus, and let's put that here, minus log of 0.0150, and this is equal to 12.18. Okay, remember that is the base that is in excess, therefore you will calculate first the pOH and then the pH. Now if you were going the other way around, if you were titrating a strong base with a strong acid, well, the results are similar except with some differences. Number one, region A, the initial pH is going to be a basic pH. You are starting with a base, right? So it's going to be a basic pH. Therefore, the base is the one controlling the pH at the beginning. Region B is between the initial pH and the equivalence point. So if you're starting with a base, then the base is still controlling in that region. The leftover base is controlling that region. Region C is the equivalence point. You're still with a strong base and a strong acid, so the pH is going to be 7. And then the last region past the equivalence point is controlled by the excess acid. But how you do the calculations? Pretty much in the same way. Okay, so let's do an example. This is how the titration curve looks like. You know, we are starting at a basic pH, you end up with an acid pH. Okay, but in terms of shape and how you work each region, it's pretty much the same. So in this case we have 35 milliliters, 0.180 molar sodium hydroxide, and we are titrating this with 0.150 molar HCl. So what is the pH before you add any acid? Well, here pH is going to be 14 minus pOH. We have an initial concentration of OH minus equal to 0.180. No need to adjust for volume because it's the same volume. Alright, so then the pH is going to be equal to 14 minus the log of 0.180. Okay, remember this is the pOH, and this is equal to 1326. Now once you have added 1575 milliliters of HCl, well, first of all, final volume is 35 plus 1575, which is 5075. Okay, 0.035075. All right, liters. So initial moles of sodium hydroxide is 0.035 times 0.80 per liter, and this is equal to 0.0063, and then for the acid is 1575, sorry, 0.1575 liters, and the concentration is 0.150 per liter, and this is 0.002363. Therefore, leftover base is equal to your initial 0.063 minus what you added of acid, 0.0002363, and this is equal to 0.003937. Okay, and this is moles of leftover base. Therefore, the concentration of the base, which is equal to the concentration of OH minus, is equal to the leftover base divided by the final volume. Okay, these are moles, these are liters, and this is equal to 0.07758. Okay, pH is going to be equal to 14 minus minus the log of 0.07758, and this is equal to 1289. Alright? Now, instead of asking what is the pH at the equivalence point, well, how much volume of HCl you need to reach the equivalence point, and this is pure stoichiometry. Okay, pure stoichiometry. And just remember the reaction is HCl plus NaOH will give you NaCl plus water, and it's a one-to-one reaction. And how do we start this? Well, we start with what we know. Okay, we have 0.035 liters of the base times 180 moles of NaOH per liter. Okay, now how much acid? Well, we need 1 mole of acid per mole of base. And what volume do we need? Well, in this case, you have 1 liter of acid with 0.150 moles of the acid. Okay? And out of this, we obtain 0.042 liters of the acid, which is pretty much 42 milliliters. So to reach equivalence, you need about 42 milliliters of 0.150 molar HCl. And when you add those 42 milliliters, then you get a pH of 7. Now in this problem, what is the pH after you added 43.25 milliliters of the acid? Okay, remember the equivalence is if you added, based on the previous problem, if you added 42 milliliters of HCl, that is what you require for to react with the base. Okay, which means 43.25 minus 42, 125 milliliters HCl in excess. Okay, so we can go with this way. I mean, you can use the initial number of moles of sodium hydroxide and calculate the total number of moles of acid that you have added, but because we have this data here already, we can use that to our advantage, and then just determine that at that point, if you reach equivalence with 42 milliliters, then if you add 43.25, then you added 125 milliliters in excess. Okay, so let's use that, and these 2 liters is 0.00125, and that's what we use, 0.00125 liters. The concentration of the acid is 0.150 molar. So we obtain 0.000188 moles of HCl. Okay, why don't I use the concentration directly to calculate pH? Well, because the volume changed. The final volume here is 35 plus 43.25, and this is equal to 78.25 milliliters. So in order to calculate the concentration now, then I have to divide this by that volume, 0.07825 liters. Okay, so these 2 liters, 0.07825. So the final concentration is 0.00240 molar, and the pH is minus log of that number, 0.00240, and this is equal to 2.62. Okay, so in summary, if you have a titration curve, you can distinguish 4 regions in that curve. Number 1, the initial pH, okay, controlled by the acid, by initial acid or base, prior to the equivalence point is controlled by leftover acid or base. The equivalence point, which we're going to have a pH equal to 7. Remember, we are working with strong acids and strong bases, and this is controlled by excess base or acid, depending on what you have. Okay, the important thing here to remember for strong acid, strong base titration is that at the equivalence point, the pH is going to be 7, and that's going to be always. Okay.